about the test. There is some problem with it, guys. Okay, test 2. There is some problem with it. Hopefully, because yesterday I didn't get time. I was just going through everything, but I didn't find time. Today also I tried. I was in journey. I was still trying. So there was a little bit of problem with test 2. Right after the class, I'll try once again. Okay, and hopefully I will share the link as soon as possible. So you can write test 2 probably tomorrow, guys. Okay. Is the board visible, all of you?
Yes, sir.
Yes.
Right. So we will begin moving charges and magnetic effects of current. Okay. I hope the board is visible, all of you. Yes, no?
Yes, sir.
Yes, sir.
Right. So as I said, there is a little bit of problem with test 2, guys. I was just trying to just check what was the problem, but unfortunately, I was not able to resolve because first major reason is lack of sleep again. So I was not able to resolve that. So hopefully I'll try my best today, guys, and I'll share the test. Okay. So don't worry about it. Definitely it will be done by today night, and you will get the test link by today night. And I'll keep it active till tomorrow evening, guys. Okay. So let us move on to the next chapter called as magnetic effects of current, moving charges and magnetic effects of current. Okay. I hope the board is visible. I am audible. Is everything all right, guys?
Yes,
Yes,
sir.
sir.
Right. Now, in this particular chapter, always remember, basically when we talk about a moving charge, a static charge, whenever a charge is at rest, it will be producing electric field. A moving charge, guys, will be able to produce both electric field and magnetic field, right? So if we talk about the magnetic field produced by the current carrying element, it was given by Biot-Savart's law, guys. So whenever you try to find out the magnetic field due to a current carrying element, it will be given as, in magnitude if we talk about, it will be given as mu naught by 4 pi I dl sine theta divided by r square. This is magnetic field due to a small current carrying element, guys. But if I want to write it in terms of vector notation, guys, so magnetic field, as you can see, it will be in the direction of dl bar cross r bar. So in vector form, it is given as mu naught by 4 pi I into dl bar cross r bar divided by r cube. And always remember, dl bar direction will always be taken in the direction of flow of current. And as you can see, the small magnetic field, it will have same direction as that of dl bar cross r bar. So what is dl bar? It is the small current carrying element. What is r bar? It is the distance or the position vector of the given point from the current carrying element. So as you can see in the diagram, dl bar is something in this manner upwards, yes or no, and r bar is like this. So I hope that you all are aware of finding out or performing cross product, guys. So because it is in the direction of dl bar cross r bar, dl bar happens to be the first vector, r bar happens to be the second vector, guys. What are we going to do in this situation? dl bar will always be in the direction of current. So let us say if current is flowing in upward direction like this, so dl bar should also be taken upwards, guys. So dl bar is like this, which is the length of the element vector. R bar is in this manner. So how will you do cross product? In the direction of first vector, we are going to place our right hand. Curl the fingers towards the position vector r bar. The direction of thumb will give us the direction of magnetic field at that particular point, guys. Clear? Actually, this is how you solve it. But from competition perspective, there is other method of doing it. I'll tell you in some time, guys. So whenever we consider Biot-Savart's law, it is used to find out the magnetic field due to a current carrying element, guys. How much is the magnetic field due to a current carrying element given as mu naught by 4 pi I dl sine theta divided by r square, right? Or if you want to write it in vector form, it is mu naught by 4 pi I into dl bar cross r bar divided by r cube. Last year, based on this vector form, right, you got one statement, Biot-Savart's law statement, guys, again. So mu naught by 4 pi I into dl bar cross r bar divided by r cube will be the magnetic field due to the current carrying element. How will you find the magnetic field? In the direction of dl bar, place your right hand, curl the fingers towards r bar. Direction of thumb will give us the direction of magnetic field, guys. Dl bar will always be in the direction of current vector. Now this is by definition of Biot-Savart's law again, or by the expression of Biot-Savart's law. But in general, how you can do is, in the direction of current, what we will do, in the direction of current, we are going to place the thumb of the right hand, guys. Where is the point? Is it to the right of the current carrying element or not? The point is to the right of the current carrying element. So what are we going to do? In the direction of current, we'll place the thumb of the right hand tangent to the curl of the fingers at the given point. So where is the tangent pointing again? Inwards. So usually for current carrying wires or current carrying elements, we will use this right hand thumb rule, guys. In the direction of current, place the thumb tangent to the curl of the fingers at the given point will be giving us the direction of magnetic field. Is that clear, all of you? Yes or no, everyone? In the same manner, SI unit of magnetic field, if I consider, SI unit of magnetic field is given by Tesla, guys. SI unit is Tesla. CGS unit will happen to be Gauss, right? And one Gauss will be 10 power minus 4 Tesla, guys. One Gauss will be 10 power minus 4 Tesla. Just give me a second. Am I audible, visible, all of you?
Yes, sir.
No, I thought someone came because I was alone at home and my mother locked the door and went. No, I was thinking, I just heard some noise. So I thought, koi chor aa gaya honga. Then I went there and saw my mother is there. I'm saying, Kunya mere paas hai, aap kahan se gaye ho? No, I came, you were explaining, I took the keys and went. The keys were here only. I didn't even notice that she has come. Right. Board visible, all of you?
Yes.
Right. Static charge, always remember, static charge will produce electric field. Moving charge will produce both electric field as well as magnetic field, guys. So whenever charge is moving, obviously there will be current. So due to a current carrying element, there will be magnetic field. The magnetic field was given by Biot-Savart's law. In magnitude, in scalar form, it is mu naught by 4 pi ideal sine theta by r square. And in vector form, it is mu naught by 4 pi, same only. But instead of ideal sine theta, I will write dl bar cross r bar divided by r cube. SI unit is Tesla, CGS unit is Gauss, and one Gauss will be 10 power minus 4 Tesla, guys. And basically, they will ask you dimensions also. If you talk about dimensions of magnetic field, I think it will be given as m L naught t power minus 2 a power minus 1, guys. These will be dimensions of magnetic field, right? So in the same manner, we are going to have some formulas again. You need to remember these formulas, guys. There are proofs for everything, but again, time constant, we cannot discuss any proof and all, guys. So please do remember the formulas again. First is magnetic field due to a finite current carrying wire. So the finite means both the ends are going to be at rest, guys. Again, both the ends have some what we can consider, they have end points again. So this is a finite wire. We are interested in calculating magnetic field at a point P, which is at a perpendicular distance r from the finite wire, guys. So how will you find direction of magnetic field? Again, very simple logic. In the direction of current, we will place the thumb. Where is the point? To the right. So tangent to the curl of the fingers to the right. So where is the tangent? It will be inwards. So inwards will be represented by cross, guys. Suppose if I say the point is to the left, what we will do, in the direction of current, we will place the thumb only. But where is the point now? The point is to the left, guys. So I will curl the fingers like this. Tangent to the curl of the fingers will be pointing outwards. So whenever current is in upward direction, magnetic field to the right point will be inwards. Magnetic to the left point will be outward, guys. Clear, all of you? Understood, everyone? So what is the magnetic field given as? Again, due to a finite current carrying wire, right? Let me not say this is theta, guys. I will just remove this. If not, you will get confused again. So I'll remove theta 2 and theta 1. If not, you will get confused, right? So I'll also remove this mu naught I 4 pi r cos theta 1 plus cos theta 2. Although it is correct formula, but I'm not going to focus on this, guys. Okay, so we are interested in finding magnetic field at point P, which is at a perpendicular distance r from the finite current carrying wire. So what we'll do, from the given point to one end, I'll draw a dotted line. From the given point to other end, I'll draw dotted lines. The angle made by these dotted lines with the horizontal will be taken as alpha and beta, and magnetic field will be given as mu naught by 4 pi r sine mu naught I divided by 4 pi r sine alpha plus sine beta. Suppose if you take a infinite wire, guys, if I am if I assume that it is an infinite wire, so you can consider magnetic field is given as, for finite wire, it is given as mu naught I by 4 pi r sine alpha plus sine beta. Very important formula, guys. If it is infinite wire, both the ends will move to infinity or not. This end will go to infinity, right? So beta is something like this, guys. Now, if this end is moving to infinity, the dotted line, will it become vertical like this or not? So beta value will become 90 degrees. In the same manner, the other end is also going to go to infinity. So other dotted line will also move to infinity, guys. So what is the angle made for infinite wire, alpha and beta, guys? For infinitely long wire, again, I'm not going to focus on theta 1 and theta 2. For infinitely long wire, what will be alpha and beta values? Alpha and beta values are going to be pi by 2, guys. So what is the magnetic field? You will get magnetic field due to a infinite wire as mu naught I divided by 2 pi r. Clear, all of you? Now, I cannot say for semi-infinite wire always it will be mu naught I divided by 4 pi r, guys. When will it be mu naught I divided by 4 pi r? Suppose if I take semi-infinite wire. Now, what is the logic behind taking semi-infinite wire? Semi-infinite means one end of the wire will be finite, right? It will have a fixed end, guys. Whereas the other point, the other end will move to infinity. Now, when will I say for semi-infinite wire? Again, I'm not going to talk about theta 1 and theta 2. As I said already, we will not be focusing on theta 1 and theta 2, guys. Right. Now, this is a semi-infinite wire carrying current in upward direction only, let us say. Now, one end is fixed, other end is moving to infinity. So when will I get mu naught I by 4 pi r beta? When the point is exactly opposite to the finite end. At a perpendicular distance, how much again? It is at a perpendicular distance of r. So when this point is exactly opposite to the finite end, see, what will alpha become again? Point P is here now. So it means dotted line will be horizontal or not? This dotted line. This dotted line, which was in this manner, will become horizontal now. So alpha will become 0. Whereas this end, this dotted line will now move to infinity, guys. So beta will become 90 degrees. Or you can say, if I say this end is moving to infinity, if the point is somewhere over here, then I'll write alpha is pi by 2, beta is 90 degrees. It is not necessary that alpha only should be pi by 2, guys. You can also write alpha can be 0, beta can be pi by 2. These two cases are possible again. But for semi-infinite long wire, remember, at only one case you will get mu naught I by 4 pi r. What is it? When the point is exactly opposite to the fixed end at a distance of r. Clear, all of you? So due to a finite wire, mu naught I by 4 pi r sine alpha plus sine beta. Alpha and beta are angle made by the dotted lines with the horizontal. For an infinite wire, both the ends will move to infinity. Alpha and beta will become 90 degrees. So mu naught I divided by 2 pi r you are going to get. Whereas for semi-infinite wire, you will get mu naught I divided by 4 pi r only if the given point is exactly opposite to the finite end, guys. Clear, all of you? Is that clear? What is the other logic if you see? Suppose, sir, what if it is not opposite to the finite end? Suppose let us say one end is finite, other end is moving to infinity. This end is anyhow finite, you can consider. Now, in the previous case, where was the point? It was exactly opposite to the fixed end. Now, I'll take the point to be somewhere over here. Although it is at a perpendicular distance, r only you can consider, guys. So, perpendicular distance happens to be r. right? It is carrying current I in upward direction only, let us say. Now in this case, what will happen? This beta angle, guys, see what we will do from the given point to the ends. I will draw dotted lines because this end is going to infinity. Here beta value will be how much beta? Beta value will be 90 degrees, whereas alpha will remain alpha only, guys. Alpha is going to remain alpha only. So if you take a this is also semi-infinite wire, but is the point exactly opposite to the fixed end? No, it is not opposite to the fixed end. So in that case, what will I write the magnitude as? In that case, I'm going to write the magnitude as mu naught I divided by 4 pi r, right? One angle sine 90 it became. Sine 90 will be, or you can write sine, one angle is alpha only, other is sine beta, beta became 90, you can write it as 1, guys. So this will be the magnetic field. Two cases in semi-infinite long wire, guys. Clear all of you? For a finite wire, mu naught I by 4 pi r sine alpha plus sine beta. For a infinite wire, mu naught I by 2 pi r. For a semi-infinite wire, two cases. If the asked point is opposite to the finite end, and if the asked point is not opposite to finite end. If the asked point is opposite to finite end, mu naught I by 4 pi r. If it is not opposite to the finite end, then mu naught I by 4 pi r, 1 plus sine theta, sine alpha, sine beta, whatever it may be. Clear all of you? Is that clear?
Yes.
Then we also have a current carrying circular loop, guys. So if you have an entire loop carrying some current I, then magnetic field will be given as mu naught I divided by 2r for a entire loop carrying current. Now please understand, guys, if it is carrying current in anti-clockwise sense, a current carrying loop will always behave as magnet. So let us say I have taken it something in this manner, right? So I am in front of the loop. Sense of the current is anti-clockwise, let us consider, guys. I am in front of the loop. So for me, the sense of the current will be anti-clockwise. But if I observe from here, see, if I just keep it like this, and I'll say the sense is anti-clockwise. So when I'm observing from the front, the sense may be anti-clockwise. I'm not changing the current, guys. But if I observe it from the back now, for me, the sense will become clockwise, guys. So always remember, a current carrying circular loop will behave as a bar magnet if the sense of current is anti-clockwise, guys. Now, for current carrying wire, how did you find the direction of magnetic field? In the direction of current, we will place the thumb. At the given point, you will draw tangent to the curl of the fingers. Whereas in case of circular current carrying wires or circular current carrying loops, guys, how will you find the direction of magnetic field? Now, sense of current, you see, in the diagram, it is anti-clockwise. So, along the sense of current, you will curl the fingers of the right hand. So, along the sense of current, curl the fingers of the right hand. The direction of thumb will be pointing outward, or the direction of thumb will be pointing inward. So whenever you have an anti-clockwise current, you are going to get a outward field, guys. And anti-clockwise current will behave as a north pole. Whenever you have a clockwise current, you are going to have a inward field perpendicular to the plane of the object, and clockwise current will behave as south pole. So I took only one loop. If I was observing from front, it had anti-clockwise current. The same loop, if I'm observing from the back, I got clockwise current. So whenever you have current carrying circular loop, you will have both north pole as well as south pole. So current carrying loop is going to behave as a magnet. If you talk about current magnetic field produced at the center due to the entire loop, it will be mu naught I divided by 2r. At axial point, what is the meaning of axial point? Suppose if I take this is the loop, guys. What is the axis again? It will be a line passing through the center and perpendicular to the plane in which the object is present, guys. Suppose if I say the object is present in xy plane, then z axis will be its axis beta. And any point on the axis will be called as axial point. So on the axis of the loop, the magnetic field, if I consider, I can just write over here. If I write it in vector form, beta, I'll get it as mu naught by 4 pi, right? 2m bar divided by r square plus x square whole power 3 by 2. This will be the magnetic field at which point, beta? At an axial point. And please do remember, right? Now, magnetic field will be in the direction of magnetic dipole moment. Now, how will you give magnetic dipole moment? As it you can see here, for one turn, if I have a loop of one turn, guys, it is given as current into area vector. And always remember, area vector will be perpendicular to the plane in which the object is present, guys. This is for one turn only. For how many turns, beta? For a loop of one turn. Suppose if I have for n turns, guys, for a loop of n turns, if I say, then how will I give magnetic dipole moment? I will give the magnetic dipole moment as m bar will be given as n I a bar. This will be the magnetic dipole moment for a loop of n turns. If you have a loop of only one turn, directly I'll write I into a bar. Okay, but if you have n turns in that loop, n into I into a bar. These two are very important, guys. Magnetic field due to a current carrying circular loop exactly at the center, mu naught I by 2r due to the entire loop. At an axial point, which is at a distance x from the center, what will it be? It will be mu naught by 4 pi 2m bar by r square plus x square whole power 3 by 2. These 2 points they will ask you. They will ask you what is the ratio of magnetic field at center to the magnetic field at an axial point which is at a distance root 3r or root 5r or root 7r. So something like this they will be asking you, guys. Clear all of you? Understood everyone?
Yes.
We'll conduct the sessions from 8 o'clock, guys, from tomorrow onwards for a few days again, as I said you before as well. For a few days, we will conduct from 8 o'clock. And don't worry about the syllabus. Please have faith in me. I'll certainly complete. I'll take whatever it may be, whether it is day, whether it is night, I'll complete. And as I'm providing the recordings also, for whom you are, again, if it is not flexible for you to attend, you can definitely check the recordings as well. I hope you have access of all the recordings, guys. Yes or no? I think in
Yes.
this class also you got in. I think it will directly get added into the folder, guys. I also don't have anything to do now. Within 2 hours, you will get the access again. Okay, clear all of you? Now let us see what is the various cases of magnetic field again. Right. So let us imagine again two cases are there. Whether they will give you due to a current carrying wire and due to a circular loop. Either it may be a complete circular loop or a part of a circular loop. Okay. Now please, very important case. Again, you see here, basic logic, if you take a finite wire, what is the basic logic? Finite wire is there. If they are asking magnetic field at this point, which is at how much distance, beta? Which is at a perpendicular distance r. So what is the logic of finding the magnetic field? From the given point, what we do, we are just going to draw some dotted lines, beta. So whatever is the angle made by these dotted lines, right? Whatever is the angle made by these dotted lines with the horizontal, or with the horizontal you can take, we will take it as alpha, we will take it as beta. Okay, so that is how we take it. Now this point came here, guys. See, as you can see in the first case, the point came here. So this dotted line will become horizontal or not? The point, where did it come? The point came below, exactly opposite to the one of the end. When the point came below, this dotted line will become horizontal. So alpha value will be 0. Beta value can be taken as beta or alpha, whatever it may be. So in that case, you will get the magnetic field as mu naught I by 4 pi r. One angle will be there, one angle will be 0. So sine 0 will be anyhow 0 only. So this will be the case, guys. Okay. Next, in the same manner. Now, as I said just now, this case I have already told you. Did I say this case or not, guys? It is which wire? Semi-infinite wire. Is the point opposite to one of the end? No. If the point was opposite to one of the end, what would have been the answer? Mu naught I by 4 pi r. But because the given point is not opposite to the fixed end, the answer will be mu naught I by 4 pi r, 1 plus sine alpha, 1 plus sine theta, 1 plus sine beta, whatever it may be. Is that clear, all of you? Yes or no, everyone? Now let us talk about this case, guys. Okay. Now this case, how can I understand this case? It's a very simple logic to understand. We have only this part, guys. I have only this part. So what I'll do to this part is I will just add and I will subtract. Did I make any change? See, I'm adding this, I'm removing this. So did I make any change, beta? You see, if I use this concept, did I make any change? I have added this and I'm removing this. Did I make any change? No,
No.
I have not made any change. So overall, what will I get? I will get, again, I can consider this to be something in this manner. Now I'll get two things, guys. I will get something in this manner and I will get a small loop again, small current carrying wire you can take. Okay, so the point is somewhere over here, point is somewhere over here, right? So okay, I'll show you in the other diagram. Okay, so what we can do in this situation is, because which angle is greater here? Alpha is greater, no? So directly I'll write mu naught I by 4 pi r sine alpha, but I need to remove this part, guys. So I'll write minus sine beta. Okay, how we are obtaining it, I'll tell you, right? I'll just take it over here, guys. But before I explain this, magnetic field will always obey superposition principle. Suppose there are different current carrying elements, guys. 4 5 current carrying elements are there, and due to those 4 5 current carrying elements, I want to find magnetic field at a point. So it is going to follow superposition principle, guys. Whenever I want to find resultant magnetic field at a given point, it will be vector sum of magnetic fields due to all the current carrying elements, guys. It will be vector sum of magnetic fields due to all the current carrying elements. Is that clear, all of you? Yes or no? So now what I did, in order to find the magnetic field due to this particular part of the wire, I have just added this wire and I am removing this wire. I am adding these two, let us say. If I'm adding these two, they both are equal and opposite in direction. Will they cancel out, guys? Yes, they are going to cancel out. So what will our effective value be is, I'll get total length something like this, and I'm going to get a small wire something in this manner, guys. For wire, I believe you know how to find the direction of magnetic field. For wire, do you know how to find direction of magnetic field, beta? In the direction of thumb, you are going to play, in the direction of current, you are going to place the thumb, and tangent drawn to the curl of the fingers at the given point will give us the direction of magnetic field at that point. Yes or no? So what I can take, this part and this part, will they entirely be current I or not? And how much is this angle? Total angle you have alpha. In the same manner, the other part is carrying current in downward direction, same current, right? And what is this angle given as? This angle is given as beta. And in both the cases, the distance, perpendicular distance from the wire is r, guys. So this is our first wire, this is our second current carrying wire. Please tell me, what is magnetic field due to first wire? Again, as you can see, it is mu naught I divided by 4 pi r, because the point where I want to calculate the magnetic field is exactly opposite to the other end. One angle will become 0, other angle will be alpha. So what are we going to get here? Sine alpha, let us say. What is the direction? Direction of current is upwards. So in the direction of current, place the thumb tangent to the curl of the fingers. Where is it pointing, beta? Inwards. So here you are going to get inwards. Whereas magnetic field at the given point due to second element, how is current now? It is in downward direction. Is the point to the left, guys? No, the point is to the right. So what I'll do, in the direction of current, I'll place the thumb tangent to the curl of the fingers at the point. The tangent will be pointing outwards. Again, you see, it is also finite wire, and point is exactly opposite to one of the end. So one angle will be 0, other angle is given as beta. So what will I get here? Mu naught I divided by 4 pi r sine beta. In which direction? Outward direction. Now what is the resultant magnetic field? It will be vector sum of b1 bar and b2 bar. So if you solve for that, no, you will get the answer as mu naught I by 4 pi r sine alpha minus sine beta in inward direction. Or I can write sine beta minus sine alpha in outward direction. Clear, all of you? Is that clear, everyone?
Yes, sir.
The same things you can apply for this part also, guys. for here, you consider this as one wire. So what will magnetic field at center be? If it is carrying current in this manner, magnetic field will be inwards. If you take this part also, current is in the rightward direction, place the thumb towards right, tangent to the curl of the finger inwards. Everywhere you see guys, the magnetic field will be inwards only. Now what will you do? In rectangle, the diagonals will be perpendicular bisectors guys. Right? No, sorry, not in rectangle. In square they will be perpendicular bisectors. So here what will I do? This distance I will take. Right? So what will you get this value as? Let us consider. So from the given point, this will be one value theta 1. Here again you will have some theta 2. So like that, what I'll do is I'll find for this part of the wire. I'll also find for this part of the wire. I'll add both of these and double the value in order to get the magnetic field. Clear all of you? I think you can find it again. It is same as the case of finite wire again. This case. Is this case, guys? Are you getting my point? All of you, it is this case. But instead of one wire, here you have 5 wires, guys. Length A, length B, length A, length B. 4 wires you have here. Here you had only one wire, but here you have 4 wires. So you need to apply Biot-Savart's law for 4 wires, guys. Clear all of you? Yes or no, everyone?
Yes.
Yes, sir.
In the same manner, again, for all such cases, you can do it, guys. You can take for hexagon, you can take for triangle, you can take for n number of cases. Now, hexagon is basically formed by 6 equilateral triangles, guys. So you take for one wire, right? And what is this distance? This will be root 3 by 2 into a height again. What will this angle be? 30 degrees. This angle will also be 30 degrees. Okay. You find due to this part of the wire and multiply by 6 times. Clear? Now, one very important point that you need to know. Here you see you have 3 parts, guys. Here you have wire, first part. Then you have curved part, second part. Then you again have wire. Now, if you look at the point, they're asking us to find magnetic field at point O, guys. Now, where is this point O lying is very important. If you produce the first wire, is point O lying on the first wire produced? Yes. If you produce the third wire backwards, is point O again lying on the third wire produced or not? So, whenever a point is lying on the current carrying wire or on the current carrying wire produced, because of that particular wire, magnetic field at the point will be 0. So here, what I can say, beta, magnetic field due to first element 0, magnetic field due to third element 0. The magnetic field will be only due to which element, beta? Second element. And is it an entire circle? No, it is a semicircle, guys. So always remember, for a part of a circle, whenever we have a part of a circle or an arc of a circle, magnetic field will be given as mu naught divided by mu naught I divided by 2r into theta divided by 2 pi. So here theta is the angle subtended by the part of the circle at the center. So how much angle it is subtending, beta? It is going to subtend pi radian. So I'll get mu naught I by 2r, pi by 2 pi, pi and pi will get cancelled, mu naught I by 4r I'll get. How will you find direction of magnetic field for a loop? Using right hand rule. For a wire, right hand rule only. For a loop also right hand rule only, guys. For wire, what will you do? In the direction of current, you will place the thumb. Tangent to the curl of the fingers at the given point will give direction of magnetic field. Whereas for a curved part, what will you do? Along the sense of current, you will curl the fingers of the right hand and direction of thumb will give us the direction of magnetic field. Is that clear, all of you? Understood, everyone?
So can we multiply by 4 after finding the magnetic field due to a single wire in the fourth case?
In which case?
In the fourth.
No, you cannot multiply by 4. If it is a square, you can multiply by 4. So what I said, that is the reason I said you find out magnetic field due to this part. You find out magnetic field due to this part. Add these two magnetic fields and multiply by 2, I said. Okay.
Understood.
If it is a square, you can do find out for one part and multiply by 4. Just like you can do it in hexagon. Find for one part of the wire and multiply by 6. Clear?
Yes, sir.
In the same manner, guys, again, one very important point that you need to know is, suppose 8th point I'll take. 9th point is also pretty clear, guys. So you have how many parts again? This is one part and this is second part. And automatically, if you take this as your third part and this as your fourth part, due to third and fourth part, because the given center is lying on the third part produced and fourth part produced. So due to third part and fourth part, magnetic field at center will be 0. The magnetic field will be due to first part and second part. Again, both are semicircles. You can find the magnetic field and you can just apply net magnetic field is vector sum of the resultant vector sum of the individual magnetic fields. Now, 8th point is very important, guys. Suppose if I take a regular uniform geometrical shaped object, regular object, guys. So circle is a regular object again. Yes or no? If you take a regular uniform geometrical shaped object, right? So circle is there. In this circle, what is happening? Into this geometrical shaped object, some I current is entering, and the same I current is leaving out. In such case, always remember, for uniform regular geometrical shaped object, if some current is entering into the center and the same current is leaving out, in that case magnetic field produced at their geometrical center will be how much, beta? 0. Clear, all of you? Yes or no? Very important point. Here it is for circle. You can take for square, you can take for hexagon, you can take for pentagon, you can take any regular geometrical shaped object. Uniform regular geometrical shaped object, if the current is appearing to enter into the center and appearing to leaving out from the center, same current is leaving out, then in that case what we can say, magnetic field due to this whole combination at the center will be 0. Same will be for cube, guys. As you can see, current is entering into the body center, right? And you can observe it is again leaving out, guys. The same current is entering, same current is leaving out, so magnetic field at the center will again be 0. Clear? For uniform regular geometrical shaped objects, if current is entering into their center and same current is leaving out, then blindly remember magnetic field at the center will be how much, beta? 0. Understood? Is that clear, everyone? These are all cases again you can do. These are all principle of superposition only. Magnetic field at any point will be vector sum of magnetic field due to all the current carrying elements. How can those current carrying elements be? As of now, they can either be straight current carrying elements or they can be curved current carrying elements, part of a circle, guys. Clear?
Yes.
Then we have Ampere circuital law. Right? So what is Ampere circuital law stating? Very simple logic. Line integral of resultant magnetic field over a closed loop would be equal to mu naught times the net current threading the loop, guys. So this is the actual formula again. So Ampere circuital law is stating that line integral of resultant magnetic field over a closed loop will be equal to mu naught times the total current threading the loop, guys. Now, which current should be taken as positive, which current should be taken as negative is very important, guys. Okay, so suppose if I take, you have a certain loop in this manner. I am taking different wires, guys. So let us imagine we have taken some 4 wires. And how am I traversing again in the loop, guys? I am traversing in this manner. So in this particular circuit, how many loops do we have? Are we able to find 2 loops or not, guys? See, this is one of the loop and this is another loop. Yes or no, all of you? Is that clear? First wire, second wire, third wire and fourth wire. Which current should be taken as positive, which current should be taken as negative? So you see this loop. How is the sense of motion in the loop? Anti-clockwise. So what I'll do, along the sense of motion, curl the fingers of the right hand. in whichever currents are in the direction of thumb, those should be taken as positive. So in this loop, sense is anti-clockwise, so I've curled the fingers in anti-clockwise sense, direction of thumb is upwards, so all currents in upward direction should be positive. So third current will be positive, so by automatically fourth will become negative. Now how is the sense in this loop? Clockwise or not? What will I do? Along the sense of current, curl the fingers of the right hand, direction of thumb will give us positive currents. So downward currents are positive, so first one will be what, beta? Negative, second one will be positive. So what is the net current that I'll write here now? I'll write minus I1 plus I2 plus I3 minus I4. Clear, everyone? Is that clear or not, everyone? Right, so what is it stating? Line integral of b bar dot dl bar over a closed loop will be equal to mu naught times the net current threading the loop. How will you take the currents? I have told you. Along the sense of motion, curl the fingers of the right hand. All those currents which are in the direction of thumb will be positive. All those currents which are opposite direction of thumb should be taken as negative, guys. Is that clear?
Yes.
Now we have ampere different applications of ampere circuit law, although they are not that much essential, guys, for a long current carrying where we know it is mu naught I by 2 pi r again, so I'm not using that. This is very important. You got this question last year, you got this question 3 years before that also, guys. Okay, exactly, I don't remember. 2016 I think it was asked. It was also asked in 2019, I believe. 2020 also it was asked, 2022 also it was asked, guys. So basically you will be asked magnetic field inside a solid current carrying conductor and outside the solid current carrying conductor. If you take a solid current carrying conductor, as of now, please remember the formulas, guys. Right, what is the magnetic field inside? It will be given as mu naught I they have forgotten here. The mu naught I divided by 2 pi capital R square into small r, guys. So this is your magnetic field where inside a solid current carrying conductor. If you take inside a hollow current carrying conductor, guys, inside a hollow current carrying conductor, there will not be any magnetic field. And outside, if I consider, you will get, if I just look at it outside, outside, okay, you can write it outside. If we are trying to find out, guys, if we are trying to find outside magnetic field outside the, you will give it as mu naught I divided by 2 pi small r. So inside it is directly proportional to r, whereas outside, if I take beta, it is inversely proportional to r. So inside it will follow which graph, beta? Because y is directly proportional to x, it will follow straight line. Outside it is inversely proportional to x, so it is going to follow rectangular hyperbola. Clear, all of you? So if they are asking you to find the plot of the graph, guys, the plot of the graph will be something in this manner. Clear, everyone? However, if you take hollow tube or hollow conductor, guys, inside a hollow tube, magnetic field is 0, because whenever we are considering a solid current carrying conductor, current will be distributed in its entire volume. For a hollow current carrying conductor, current will be distributed only on its surface. So if you take a point inside the current carrying tube, guys, we are not going to have any magnetic field inside. Outside will be same as that of your solid conductor, guys. So inside, please remember mu naught I by 2 pi small r divided by capital R square. Outside it is mu naught I divided by 2 pi small r. Understood, all of you? Yes or no? Please remember the formula. The variation is something in this manner. Clear?
Yes.
Right. If you take a solenoid, what is solenoid, guys? Again, it is simply a coil, as if we want to say, it is simply a coil, guys. Right. Although all the things are not given here, I'll just write all the things, guys. If you take an infinite solenoid, means this end is going to infinity, this end is also going to infinity. Magnetic field anywhere you take in between, it will be mu naught Ni. Small n is the number of turns per unit length, guys. So small n can be written as capital N divided by L. Small n is number of turns per unit length. Capital N will be total number of turns. L will be length of the solenoid. So if you have a infinitely long solenoid, right? You take any point inside, guys, you will have a magnetic field which is equal to mu naught Ni. It is a uniform magnetic field. And if we are taking an infinite solenoid, if I want to find magnetic field at one of the end, guys, then it will be given as mu naught Ni divided by 2. Okay. This is for which solenoid? This is the situation for infinite solenoid or a solenoid of infinite length. It is also called as your long solenoid, guys. What if I am taking a finite solenoid? Again, it is simply a coil, guys. What if I am taking a finite solenoid? Something like this, right? You can assume this to be the axis, guys. And our interest is to calculate what is the magnetic field somewhere over here. What I'm going to just what we did in your current carrying wire, the same thing we are going to do, guys. From the given point to one of the end, draw dotted lines. From the given point to the other end, draw dotted lines. So are they going to make some angles or not? So with horizontal, angle made will be alpha and beta. So what would be the magnetic field here, guys? Magnetic field at point P will be given as mu naught Ni divided by 2 cos alpha plus cos beta. Clear, all of you? Mu naught Ni divided by 2 cos alpha plus cos beta will be the magnetic field for which type of solenoid, beta? For a finite solenoid of length L, capital N number of turns and smaller number of turns per unit length. Clear, everyone? Yes or no? So from here to here, again from axis to the point, you can take it as equal to radius only. And this will be some length. It is a finite solenoid again. Understood, all of you? Is that clear? If you have an infinite solenoid, what is the magnetic field at the center? Any point inside you take uniform magnetic field, mu naught Ni. And if you take at any end, mu naught Ni by 2. If I take a finite solenoid, guys, and if they are asking me to find what is magnetic field at the center, so what will I write? It will be mu naught Ni by 2 cos alpha plus cos beta. Understood, all of you? Yes or no? Let us try to find out what is force on a moving charge, guys. Now, a moving charge till now, moving charge was producing magnetic field and we were trying to find out the expression for the magnetic field. But from now, a moving charge is placed in some external magnetic field, guys. So when a moving charge is placed in some external magnetic field, it is going to experience some force, guys. So that force will be given as, here simply they have given Q into V bar cross B bar, guys. But I will say the magnetic force will be given as plus or minus Q into V bar cross B bar. So I can say magnetic force is definitely going to be in the direction of V bar cross B bar. It will be in the direction of V bar cross B bar if the charge is a positive charge. If it is a negative charge, guys, then it will be opposite to the direction of V bar cross B bar. How to find A cross B? You have understood or not, guys? If I take only the magnitude, guys, I am going to get it as QVB sine theta. And what is theta here? Theta is the angle between V bar and B bar. It is the angle between V bar and B bar. Clear? Now please remember, very important points, guys. Whatever magnetic force we are getting, it will be perpendicular to the velocity vector. Whatever magnetic force you are getting, it will be perpendicular to the magnetic field, guys. So whenever two vectors are perpendicular, what will their dot product be? 0. So magnetic force and magnetic field, again dot product, how much will it be beta? 0. Clear all of you? So whatever magnetic force we are getting, it will be perpendicular to both velocity vector and magnetic field vector. So whenever we do dot product of magnetic force and velocity of the charged particle, 0. Magnetic force vector and magnetic field dot product, 0. If it is a positive charge, it will experience a force in the direction of V bar cross V bar. If it is a negative charge, it will experience a force opposite the direction of V bar cross V bar. In the same manner, as you can see, whenever both electric field and magnetic field are present, the net force will be given as, again he has not given a term plus or minus q, guys. So you will write it as q into E bar cross E bar plus V bar cross V bar. Is that clear, all of you? Yes or no?
Yes.
Right. So this expression is called as Lorentz force, guys. Okay. So what is electric force, beta? Just like we have written magnetic force as q into V bar cross V bar. If I take electric force, what will electric force be? Whenever a charged particle is placed in an external field, you will get it as, if it is positive charge, in the direction of field. It is a negative charge, it will be opposite direction of field, guys. Clear, everyone? Now some cases are there which are very, very important. Again, first of those cases is motion of a charged particle in uniform magnetic field we are talking about, guys. So how should the motion be? First case is velocity vector is perpendicular to magnetic field. So when velocity is perpendicular to magnetic field, here theta value will be how much, beta? 0. What is magnetic force? We got QVB. So when velocity is perpendicular to magnetic field, always remember, force you will get perpendicular to velocity vector as well as magnetic field, and the charged particle is going to perform which part, beta? Circular path. It is going to perform uniform circular motion. Okay. So what we can say, because it is performing uniform circular motion, so you can write here, the charged particle performs uniform circular motion. And in uniform circular motion, what will remain constant, beta? Speed is going to remain constant. So circular motion it is providing. So necessary centripetal force has to be provided by the magnetic force. So please remember, radius will be given as mv by qb or p divided by qb or 2km divided root over 2km 2mk divided by qb, guys. Okay. Now because it is executing uniform circular motion, its speed will be constant. Kinetic energy will also be constant, right? Magnetic force will always be acting along the radius. Its small displacement will always be along the tangent. The work done by the magnetic force will be how much, beta? 0. What is not changing? Speed is not changing. But see, direction of velocity is changing, guys. So again, very important point. Velocity and momentum will change. How they are going to change? They are going to change in direction, but magnitude they are going to remain same. So you also have time period of revolution. It is given as 2 pi r by v. However, please remember, it may be given as 2 pi r by v, but just like capacitance is given as charge by potential difference, it is neither depending on charge nor on potential difference. In the same manner, time period is just expressed as 2 pi r by v, but it will neither be dependent on radius nor on speed. It is given as 2 pi m divided by qb, and frequency of revolution will be qb divided by 2 pi m. Is that clear? When velocity is perpendicular to magnetic field, angle between velocity vector and magnetic field vector will be 90 degrees. Magnetic force will be given as QVB. Here, the charged particle will perform circular motion, uniform circular motion. So because it is performing uniform circular motion, what will remain constant, beta? Speed will remain constant. However, velocity will be changing, right? Momentum will also change. They will change in direction, guys. Clear, all of you? So time period will never be depending on radius. It will not depend on speed also. It will depend only on mass, charge, and magnetic field, guys. Clear, everyone? Now, second case is if V bar is at an angle theta to B bar, guys. I'm not explaining the exact how it is helical path and all, guys. So particle is going to perform helical motion. It will perform, see, V sine theta will be responsible for circular motion, guys. It will be responsible for circular motion. V sine theta is responsible for circular motion. And V cos theta is responsible for horizontal motion, guys. Is responsible for horizontal motion again. So is it performing circular motion? Yes. Who is responsible? V sine theta. In the previous case, who is responsible? V is responsible. Now what is responsible? V sine theta is responsible. So what we will write? Radius of the circular path will be mv sine theta by qb. Whatever may be the speed, whatever may be the radius, will time period depend, guys? No. The time period will be 2 pi m by qb only. However, because it is also performing horizontal motion, so how will the motion be, beta? It will be helical path. So it is going to perform circular motion as well as horizontal motion, guys. Right? So because it is responsible for horizontal motion, the displacement covered in horizontal direction will be called as pitch beta, and pitch will be given as v cos theta into capital T. Clear, all of you? Pitch is what? It is the horizontal displacement attained while you complete one circular motion, guys. And you will also have one more formula for radius of curvature. It will be given as mv divided by, you can write qb sine theta. Radius of circular path is mv sine theta by qb. But radius of curvature, if they are asking, right? Radius of curvature, if I take beta, it will be given as mb divided by qb sine theta. In radius of circular path, sine theta in numerator. In radius of curvature of the helical path, sine theta will be in denominator. Clear, all of you? Is that clear, everyone? So here, what is theta? Theta is theta only, guys. The third case, if you look at, the third case is if charged particle is moving parallel or anti-parallel, right? So in this case here, either theta is 0 or theta is 180. Will there be any magnetic force? No, there won't be any magnetic force. So that is the reason there is no external force which changes the motion of the charged particle. The path followed will be a straight line only. Clear? It will follow a straight line only. Understood, all of you? Right? So four cases in motion of a charged particle: when velocity is parallel to magnetic field, no magnetic force. When velocity is anti-parallel to magnetic field, again no magnetic force. However, if velocity is not perpendicular to magnetic field, it is at a certain angle theta, then what will you write? Radius of circular path will be mv sine theta by qb, right? Radius of helical path or radius of curvature will be mv divided by qb sine theta. Time period will neither depend on speed nor on distance. It will be written as 2 pi m by qb. And because while it is also performing horizontal displacement, in one complete circular motion, there will be some horizontal distance covered called as pitch, which is 2 mv cos theta divided by how much, beta? V pitch will be v cos theta into what is this? How much did we get time of flight? 2 pi m divided by qb we got or not? So pitch will be 2 pi m v cos theta divided by qb, guys. Clear, all of you?
Yes.
Just a second. Am I audible, visible, all of you?
Yes, sir.
Right. So till now we have discussed regarding, we have seen that whenever a charge is moving, there is a magnetic field produced. Magnetic field produced by a current carrying element will be given by Biot-Savart's law, which is mu naught I by or mu naught by 4 pi I dl sine theta by r square. Scalar form we have seen, vector form we have seen. What is magnetic field due to a finite current carrying wire, infinite current carrying wire, semi-infinite current carrying wire? What will be magnetic field at a point due to a current carrying wire if the point is lying on the wire or on the wire produced? Is all we have seen. Similarly, we have seen what is magnetic field due to a current carrying circular loop also. For full circular loop, what is magnetic field? Right? At axial point, what is magnetic field? Due to part of a circular loop, what is magnetic field? These three things we have seen. Apart from that, we have also discussed regarding superposition principle again. If you have different current carrying elements and they're asking you to calculate magnetic field at a certain point, guys, what will magnetic field be given? The magnetic field will be given how much? It will be vector sum of magnetic field due to all the current carrying elements, guys. So B resultant will be B1 bar plus B2 bar plus B3 bar plus so on again. Clear, all of you? So that we have discussed. We have also seen solenoid. We have taken Ampere circuit law. What is the statement of Ampere circuit law? We have discussed. Line integral of resultant magnetic field over a closed loop will be mu naught times of net current. Which current should be taken as positive, which current should be taken as negative, also we have discussed. And one application of Ampere circuit law, which is magnetic field due to a solid current carrying conductor. So inside it will directly be proportional to R, outside it will be inversely proportional to R. For hollow conductor, no magnetic field at all inside. Then we have seen solenoid, where magnetic field inside a infinite solenoid will be mu naught small n into I, or mu naught capital Ni divided by L. Similarly, at one of the end, it is mu naught Ni by 2. So for finite solenoid, I gave you extra mu naught Ni by 2 cos alpha plus cos beta. Then we moved on to if charge is moving. That was one part, guys. Calculation of magnetic field produced by moving charge was one part. The second part is if charge is moving in an external field, how much force it is going to experience? It will be given as plus or minus q into v bar cross b bar. If electric field is also there, it will experience a force plus or minus q into e bar. Plus, what does it indicate? A positive charge will experience a force in the direction of v cross b if electric field is there in the direction of e bar. And a negative charge particle, if it is moving in a magnetic field, it will experience a force opposite to the direction of v cross b and opposite to the direction of electric field, guys. So we got the expression for Lorentz force in that case again. Then we studied motion of a charged particle. The velocity can be projected perpendicular to magnetic field. The velocity can be given at a certain angle to magnetic field, or the velocity only may not be given, guys. Now, so in that case, we got radius, first case, radius, we got time period, we got frequency, we got all these things we have seen, guys. Now, there are some rules that you need to understand, guys. When will it complete full circle? When will it not complete full circle? Suppose if I say there is a large magnetic field, charged particle is already present in magnetic field, and you are giving a speed perpendicular to magnetic field. How is the magnetic field? Large magnetic field. Charged particle is already present in magnetic field. If you are giving a speed perpendicular to the magnetic field, it will complete full circle. But as you can see here in this case, is charged particle already present in magnetic field? No, it is entering magnetic field perpendicularly. Very important point. When it is entering magnetic field perpendicularly, it is again going to leave out perpendicularly only. So what is the deviation here? 180 degrees will be the deviation, guys. So for how much angle will it be in magnetic field? For pi angle, 180 degrees. So I'll write mu naught I divided by, so radius anyhow will be in all cases mv by qb. Whether it is entering, whether it is already present, irrespective of it, whatever angle it may be entering, radius will be mv by qb only, guys. So what is time period? Entire time period, what did I get? We got 2 pi m by qb or not? So what is 2 pi here, Bedna? It is the angle subtended at the center or not in one full cycle. But here Charged particle is not already present in magnetic field. It is entering magnetic field perpendicularly. So it is again going to leave out the magnetic field perpendicularly only. So in doing so, how much angle it is subtending at the center? Pi only. So I'll get time period of revolution in first case as pi m divided by qb. See, is it given? Yes. Similarly, here if I say if it is entering by making an angle theta with vertical, again it will leave out by making an angle theta only with respect to vertical. Let us say if it is making an angle theta with horizontal, again it will leave out by making an angle theta with horizontal only. In all these cases, radius will be mb divided by qb itself, guys. Depending on how much angle they are subtending at the center, their time periods are going to change. Clear, all of you? Yes or no? Similarly, one more application we have over here, which is suppose again you see in this case, guys, these two cases are very important again. Is how is the magnetic field? Is it large? In this case, no. It is finite. It is limited to some thickness which is d. And is charged particle already present in magnetic field? No. Again, you see charged particle is entering perpendicularly. So what they are saying, how much should be the width of the magnetic field such that a charged particle entering perpendicularly will not collide with the screen. When will it not collide with the screen, beta? If the distance value is more than radius, or if it is more than mv divided by qb, then it is not going to hit the screen, guys. Why? Because when it enters perpendicularly, is it again going to come out perpendicularly only or not? So what is the possibility? While it is entering, it will just touch and come out, guys. So when will it not hit the screen? If the distance or width of the magnetic field is how much, beta? More than radius, which is mv by qv. Or I can also write the strength of the magnetic field should be greater than mv divided by qt. Clear, all of you? Yes or no? When is this situation? When d is greater than r. Suppose in this case, if d is less than r, then will it collide, beta? Yes, certainly it will be colliding. So in this situation, please remember the deviation formula, beta. The deviation value will be given as sine inverse d divided by r. R, you know, it is mb divided by qb. So you'll get it as sine inverse of qbd divided by mb. Is that clear? So whenever width of the magnetic field is not sufficient enough to complete semicircle, then it will undergo some deviation. That deviation is given as sine inverse of d by r or sine inverse of qbd divided by mv. Is that clear? Yes or no? See, three things you remember, guys. Charged particle, you have long magnetic field. Charged particle is already present in magnetic field. If you are giving a speed perpendicular to the magnetic field, what will happen? It will complete circular path. Now, second case, what is happening? Suppose now magnetic field is not large, guys. Magnetic field has some significant thickness. Charged particle is not already present. Charged particle is entering. So depending on the thickness of the magnetic field, it may enter perpendicularly, it may leave out perpendicularly, right? And what we can consider, if it is entering by making a certain angle theta, it will again leave out by making the same angle theta. So like this we can find out, guys. Large magnetic field, charged particle already present in magnetic field, if speed is given perpendicular, full circle. Right? Now magnetic field is confined enough to some region, guys, in such a way that this distance is more than radius. Right? So whenever charged particle enters by making an angle theta, it will again going to leave out by making the same angle theta. When will this happen? If the width is more than radius. But if the width is less than radius, guys, then certainly what will take place? Collision will take place between the charged particle and the screen. Understood, all of you? Yes or no? In the same manner, we have a device which works on the first case of uh, force acting on a moving charge, guys. Right? Cyclotron is a device which is used to accelerate charged particles, guys. It will be using both electric field and magnetic field. What is the use of electric field? Electric field will increases the speed of the charged particle. What will magnetic field do? It will ensure that charged particle performs circular motion. So here the electron, not only electron, guys, the speed of the charged particle will be increased by electric field. And what will magnetic field do? It will ensure that the charged particle is performing circular motion. Clear? Now, whenever charge is moving, will there be some current or not? So, no, beta? Yes. So, what is the force on a current carrying conductor in uniform field? So we have seen what is the force acting on a moving charge placed in uniform field. In the same manner, we will see force on a current carrying conductor, guys. It will be given as I into L bar cross B bar, or it will be written as I into B into L sine theta. Directly, you can remember the net force will be given as B into, I'm not writing vector form here, guys. It will be given as B into V into L effective beta. Directly effective length between 2 points you should take. Clear, all of you? So you can use this formula, and some applications have been given. You can directly understand them. This force on a current, whenever there is a moving charge. Charge is moving means obviously current will be there. So this is force on a current carrying conductor placed in a uniform field, guys. It is given as not BVI, VVL effect. You can write it as B into I into L effective, guys. BVL effective is induced EMF again. So just like EMF, we can write it motional EMF again. Just like motional EMF is written as B into V into L effective, the net force acting on a current carrying conductor can also be written as B into I into L effective. What do I mean by L effective? It is the direct distance between the two ends across which the magnetic force is asked to be calculated. Clear, all of you? Yes or no?
Yes.
Right. So basic things you can find out, and always remember, guys, because it is cross product, force will be just like we wrote Q into V bar cross B bar. Force was perpendicular to velocity vector. Force was also perpendicular to magnetic field. In the same manner, here also force is represented as cross product, guys. The force will be perpendicular to the length vector. Fourth will also be perpendicular to the magnetic field, guys. So if you do dot product of force and length vector, 0. Dot product of force and magnetic field vector also 0. Clear, all of you? Yes or no? Then we have a current carrying loop, guys. So in general, please remember, we'll majorly focus on uniform field, guys. So I'm directly writing some cases here instead of explaining all these things again. Just now we have seen, if you take a current carrying loop, one side you may have north or south pole, other side you may have south or north pole. So whenever north and south is there, it will behave as a bar magnet, guys. Okay. So if we talk about current carrying loop, so basically we are considering a current carrying loop in uniform magnetic field. So here in first case, always remember these points, you remember sufficient, guys. Net force will always be 0. Right? In the same manner, net torque, will it be 0? No, it may be, may not be, but it is given as M bar cross B bar, guys. What we'll write it as? You can also write, if I take only magnitude again, it is given as magnitude of M bar cross B bar, which will be how much, beta? M into B sine theta. Clear, everyone? Where theta is the angle between M bar and B bar. Then it will also store some potential energy. The potential energy stored will be given as minus M bar dot B bar, guys. Or you can write the potential energy as minus MB cos theta. Clear all of you? Then they will ask you, what is the work done in rotating this loop from some position theta 1 to position theta 2? So always remember, work done will be change in potential energy only. So it will be given as mb into cos theta initial minus cos theta final. Clear all of you? Now, what is net force 0? Always remember, whenever current carrying loop is placed in a uniform magnetic field, net force will always be 0. Net torque may be 0, may not be 0. So because net force is 0, we are going to have how many types of equilibrium, beta? 3 types of equilibrium. What are these? Stable equilibrium. Here theta value should be 0 degrees. Then you have unstable equilibrium. What is theta value, beta? 180 degrees. And you are going to have neutral equilibrium. What is theta value, beta? 90 degrees. Is that clear? So whenever a current carrying loop is placed in a uniform magnetic field, net force illa. Never force, guys. Torque may be there, may not be there. The same thing, if I take a current carrying loop and place it in a non-uniform magnetic field, force will definitely be there. Torque again may be there, may not be there. Clear all of you? Yes or no? These 4-5 questions, 4-5 concepts only will be asked. Clear all of you?
Yes, sir.
Let us talk about force between two current carrying wires, guys. Now, whenever two wires are carrying current in same direction, two parallel current carrying wires we are taking, if they are carrying current in same direction, they will attract each other. If they are carrying current in opposite direction, they will repel each other, guys. And remember, force per unit length will be given as mu naught I1 I2 divided by 2 pi r. What is r here? It is the perpendicular distance between the wires, guys. Clear all of you? Right? If I want to find for some length, what I'll do, I'll multiply this part into length, guys. This is force between two parallel current carrying wires. Although they will not ask you force between two perpendicular wires, but general way you remember, guys. Right. Now, what will be magnetic force between two current carrying wires? It will be given as mu naught I1 I2 divided by 2 pi, guys. Right? You will write ln of what is the far end distance from the wire? D plus L or not? D plus L divided by what is the nearest distance of the wire, of the second wire from the wire? T. This will be the answer, guys. Force between two perpendicular current carrying wires will be mu naught I1 I2 by 2 pi ln of D plus L divided by T. Clear, everyone? Yes or no?
Yes.
Right? So please remember, two parallel current carrying wires, if they are carrying current in same sense, then attractive force. If they are carrying current in opposite sense, then repulsive force, guys. Clear, everyone? Then we have talked about ammeter, we have talked about voltmeter, we have talked about potentiometer. We have one more device called as moving coil galvanometer, guys. So what does moving coil galvanometer do? It will measure small currents through the coil, both AC as well as DC, guys. So what we will do, it is again, it will work on which principle, guys? It is going to work on a principle that there will be torque experienced by a bar magnet placed in a uniform magnetic field or non-uniform magnetic field also. So what you can say, when a current coil is suitably placed in a magnetic field, torque acts on it. So it is given by torque experienced by a bar magnet placed in a uniform field or non-uniform field, guys. So 2 points you need to remember in moving coil galvanometer. The poles will be concave shaped poles, guys. Okay, we will use concave shaped poles, right? And in the same manner, what we have, you can, this is the construction of moving coil galvanometer, you can remember it, guys. So it is depending, what is the principle of working of moving coil galvanometer? Torque experienced by a current carrying loop, guys. So what is the torque it will experience? If I go by the basic logics again, it is going to experience N into I into A into B. Yes or no? Yes or no, all of you? Now this is
Yes.
the torque which it has been experienced. So this torque will also provide some restoring twist, guys, again, to which I can represent it as C theta. So from there, theta by I value will be called as current sensitivity, and theta by V value will be called as voltage sensitivity, guys. Clear, all of you? How can you increase the current sensitivity? Previous year question again. Current sensitivity can be increased by increasing the number of turns. By increasing the number of turns, can you change the voltage sensitivity? May change, may not change, because resistance again will be depending on number of turns, guys. Clear, all of you? Yes or no? Is that clear, everyone? All of you guys, is it clear?
Yes.
Right. Biot-Savart's law, Ampere circuital law, solenoid, force acting on a moving charge, then some basics of cyclotron we will see, motion of a charged particle, force between two parallel current carrying wires, force between two perpendicular current carrying wires. Then what do we have, guys? We have torque acting on a current carrying loop, right? We have potential energy expression also for that. Then what do we have? Force between two perpendicular wires is done, torque is done. Then based on torque experienced by a current carrying loop, we have working of moving coil galvanometer. What will be used? Concave shaped poles will be used in order to produce radial magnetic field, guys. The two terms are there. One is the torque produced will be again equal to restoring torque. So you will get theta by I value will be current sensitivity, theta by V value will be voltage sensitivity, guys. So these points we have discussed in moving charges and magnetic effects of current. Is that clear, all of you? Yes or no?
Yes.
Right. So we will end the session today here itself, guys. Maybe tomorrow we can take some time extra. So I've given a review of moving charges, and hopefully within some time I will also share. I'll just check the corrections in the paper, and I'll quickly share it so that those who are nocturnal people can do the paper now. Those who want to do it in the morning can do the paper in the morning. I'll keep that paper active till tomorrow 7:30, guys. Clear, all of you? Is that clear, everyone?
Yes.
I've tried to give review of moving charges. Right, tomorrow we'll solve questions of moving charges and magnetic effects of current. In the meanwhile, during whatever time we are getting, whatever time you will get, you can please write the test of electrostatics and current electricity. Test will be easy to moderate. I am not going to give difficult questions at all, guys. Okay, please focus on scoring 80 to 120 marks in physics for sure. Okay, that's it from my end for today. We'll meet in next session. Take care, everyone. Thank you all.
Thank you.